Hello, everyone, and welcome to the third session of our AI Researcher Bootcamp. In this session, I have chosen the topic of convolutional neural networks, and I wanted to basically read one of the first seminal papers that uh, came out in this field, and I wanted to understand how the field has evolved since. So, this particular paper dates back to 1989, and it was published in the Journal of Neural Computation. Uh, it's The title of this paper is "Back Propagation Applied to Handwritten Zip Code Recognition," and the authors seem to be working at AT&T Bell Laboratories in the US. Of course, you can recognize Ian LeCun as the first author of this particular paper. So, this paper interested me a lot because it came out almost 3 decades ago and really laid the foundations of the CNNs which we are seeing right now being implemented uh, on a regular basis and part of machine learning curriculums and coursework. But these guys were one of the first people who actually came up with this algorithm, and I wanted to get an insight into their mindset and what the thought process was before even writing this paper. Uh, Obviously, at that time, AI was a very, very evolving field, and no one knew where this could go. So the research, as such, was uh, very much based on what has happened in the past and then trying to improve it instead of going in a specific direction or developing a particular application. Okay, so let's read the abstract of this particular paper first. So what this paper says is that it demonstrates how constraints can be integrated into the backpropagation network through the architecture of the network itself. So this approach has been used to recognize handwritten zip code digits, which are provided by the US Postal Service. So there is no mention of convolutional neural networks as such, but the way the authors have specified it is such that they want to integrate constraints into the backpropagation network, and they have developed a completely new architecture. So we are going to forget everything that we know about CNNs, let's say, and then try to look at this paper from a fresh start. Okay, so let's go through the introduction. What I have seen in this introduction of this particular paper is that most of the works date back to 1987. So, in a sense, this was a very, very niche field at the time. It doesn't date back to 70s or 60s, but probably the research around this space started in 85 or 86. And these guys were one of the pioneers in this particular field. Okay. So, one of the main arguments in this particular paper is that the design principle, when you are constructing the architecture of a neural network, should be such that the number of free parameters in the network should be as low as possible. And they say that application of this principle increases the probability of correct generalization because it results in a specialized network architecture which has a reduced entropy. Uh, and they have applied this principle and the backpropagation algorithm to a real world problem. So instead of handwritten digits, they have taken handwritten zip code digits, which are actually provided by the US Postal Service. Keep in mind that back then the computational powers of the machines was also not very high. Uh, so let's keep the decade and which era this paper was published also in mind as we go through the different paragraphs. Okay, so this is where the data is obtained from. The data is obtained from the US mail, which is passing through Buffalo in the New York post office. Examples of these images, as you can see, these are some of the images which are handwritten by people uh, as a postal code in the US mail system. Uh, right. So let's look at the last point of this particular data set, where they say that both the training and the testing set contain numerous examples that are ambiguous, unclassified, or even misclassified. Okay. So they have done a pre-processing step here where each digit image is typically around 40 by 16, and they have performed a linear operation to bring the image size down to a 16 by 16 pixel image. So this transformation basically preserves the aspect ratio of every single image that we have in the data. You can refer to this as well as uh, the sample image. So it has 256 image input units. It's because the image has been brought down to a scale of 16 by 16 pixels. Okay, so let's move on to the next, which is uh, the network design. So the remainder of this recognition is entirely performed by a multi-layer network. All of the connections are adaptive, heavily constrained, and trained using back propagation. You might have noticed that this word heavily constrained is being repeated multiple times. Initially, I did not know what is the meaning of this particular words, but we'll we'll come to the meaning in more detail as we go along. Another interesting thing here is that the input of this network is a 16 by 16 normalized image. I think this was the first time in the history of neural networks or image processing that an entire image was fed as an input. Previously, the vectors were provided as the input, or the features were extracted manually and then they were provided as the input. The radical change that this paper brought into the system was that it allowed you to feed the entire image in the input for the neural network. And that's what makes this design so useful, because it removes the manual pre-processing completely out of the equation. Okay, let's try to move into the next section, which is feature maps and weight sharing. So what exactly is the meaning of these two? Classical work in visual pattern recognition has demonstrated the advantage of extracting local features and combining them to form higher order features. So if you have used classical network, convolutional neural networks or CNNs before, you might be aware of these words which are called feature maps. So let me try to explain this in simple terms. Um, so feature map is basically where, let's say you have an image. It's a handwritten digit. Let's say it's a 1, 2, 3, 4, 5, etc. What you're trying to do is that you're trying to extract different features out of this particular image, which might be, let's say, vertical edges, or it might be individual components, horizontal edges, boundaries of different components which are present in that image. So features are what make the entire image. So if you have to classify an image, it makes a lot of sense first to extract all the features and then make sense of the features. We'll also see this in detail as we go along. Just keep this word called feature maps in your mind before we move ahead. The next word that you see over there is called weight sharing. Now, this is something which I think was one of the main things that was implemented uh, in this particular paper. So, they say that weight sharing not only greatly reduces the number of free parameters, but also can express information about the geometry and the topology of the task. So we are going to look in detail what is the meaning of weight sharing and how exactly uh, does it benefit the convolutional neural network. Okay, now we come to the main part, which is the architecture. This is the point where this paper completely distinguished itself from the literature which has been happening since then, and it became the cornerstone paper for all the future CNN works that we have seen. So I read this paragraph multiple times, and I try to make sense of um, what they have written over here using some using figures. So let me try to go over to Canva and help you understand exactly what is happening in the architecture. Okay, so we are going to start drawing. Okay, so let's start with the first paragraph. So the network is represented in figure 2. Its architecture is a direct extension of the one proposed in LaCun 1989. The network has three hidden layers, H1, H2 and H3. So we are going to look at these three layers separately. Let's look at H1 first. Okay. So let's see. Now we are going to go down. This is where the figure is drawn, which makes the representation of H1 more clear. So let's try to see what is happening here. So let's see the input image that we have. I'm going to draw at the bottom. The input image is basically 16 by 16, and H1 has 12 units basically, or um, 12 different components. So let me mark this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And we are going to name this as H1. Okay, so let's try to think what do these individual components represent. So we are going to look at one different component. There are 12 of these. Every single component here is basically a feature map of the existing figure. What does that mean? Imagine that you have a kernel. A kernel is a filter which goes over the entire image and it produces uh, a different image. So in this case, they have taken a 5 by 5 kernel. So what happens is that this is called as a convolution operation. We take this kernel and we slide this over this entire image, and we get a new image. Now what's happening here is that the original image is 16 by 16. What these people have done is that they have slid this kernel across the entire image by keeping a gap of 2 in the horizontal and keeping a gap of 2 in the vertical. What does that mean? That means that you have essentially a figure. So originally it had 16 by 16. Now you divide that by 4. So you will have totally 64 units, which is what is mentioned over here, 64. So basically you will have an 8 by 8 size image after you do the convolution operation and pass this filter over the entire image. So now this particular component in the H1 layer represents a feature map of size 8 by 8, which is totally 64 units. So how many units are present in H1? 64 into 12, which is equal to 768. The first hidden layer has 768 different inputs or different units. Okay, so now let's come to the point of weight sharing. When you are in this operation, when you are doing this operation, when you are sliding the kernel over all the different pixels of the image, these these components in these metrics, they are called as weights. These are the weights of the neural network which you are going to train. Now in this entire operation, you have the flexibility of either keeping these weights constant or completely changing these weights for every single pixel. What they have done here is that there are 25 sets of weights which are constant for all. So as the kernel is sliding over, here the weight is constant, here. All these points, the weights will be exactly the same and they will be 25 in number. So how many number of weights will have totally over here? 25 for the first component into 12, which would be 300. Plus there will be biases for every single component. There will be a different bias, so every single unit will have a bias of its own. So there will be 300 plus 768 biases. So overall we have 300 weights and 768 biases. Let us also confirm that as we move into the paper, but just keep this architecture in mind. We are again going to read the section in detail. Okay, so H1 is composed of 12 groups of 64 units each, arranged as 12 independent 8 by 8 feature maps. 8 by 8 feature maps and 12 independent. Okay, that makes sense. Each unit in a feature map takes input on a 5 by 5 neighborhood on the input plane. For units in layer 1 that are 1 unit apart, the receptive fields are 2 pixels apart. This is what we saw in this particular representation. The gap between um, the receptive fields is 2 pixels. That is why it is undersampled. From 16 by 16, you get 8 by 8. The reason for this undersampling is because while high resolution may be needed to detect the presence of a feature, its exact position need not be determined with equally high precision, which is what they mention here as well. Exact position of the feature is not important. You just need to know that the feature is present. For example, if I'm detecting the number 2, it's not important where uh, or which pixels are occupied by the number 2, but it's important to realize that it's the number 2. That's why the number of units in the feature maps are different from the number of units in the actual digit. uh, yeah, so now let's come to the next one, which is so it says that therefore corresponding connections of each unit in a given feature map are constrained to have the same weights. In other words, each of the 64 units in H1 uses the same 25 weights. Of course, units in another map share another set of 25 weights. Each unit thus has 25 weights plus a bias. This is what we saw in our diagram. These 25 weights remain exactly the same for this entire operation. However, for these individual units, these 25 weights are going to be different for these individual components. And uh, I'm trying to understand why this weight sharing was such a innovative idea at the time when this paper was released. It's because it allowed you to impose constraints on the network. It allowed you to fix the weights, and I think this also improved the training time of the entire network. So this was about the first layer. So as we saw, totally there are 1068 free parameters, which is 768 plus 25 into 12. Right. And then subsequently we move to layer H2 and then we move towards layer H3. We'll try to see layer H2 in a bit more detail as well. Okay, so now what we are doing in layer H2 is basically quite similar to what we did for layer H1. Let's try to write this separately. So layer H2 is again going to have 6, 7, 8, 9, 10, 11, 12. 12, 12 different components. Now, the main difference is that let's look at the first component. This first component is going to be convoluted with the entire H1 layer, which has how many units? Which has totally 12 different components. This was different from what was happening previously. H1 was connected to only the input image. But now, here the individual component is connected to 12 different components in the layer H1. So H2 is connected to 12 different. So now, just imagine what is the size of the kernel that we need. To slide across one image, we need 5 by 5. But now we need 5 by 5 by 12 if the kernel is going to slide across all the components in the layer H1. So the kernel is essentially going to be a three-dimensional kernel in this case. So what are the number of weights then for each unit? The number of weights are 25 into 12, which is 300. 300 into 12, which is around 3600. These are the number of weights which are significantly higher if you compare this with the first layer. And the reason it's higher is because the network is learning some deep representations in the process, and it's trying to understand more and more features as we are going deeper into the network. Let's try to read. So layer H2 is also composed of 12 different maps. Each feature map contains 16 units arranged in a 4 by 4 plane, H21, H22, H212. The connection scheme over here, you can see that each unit in H2 combines local information coming from 8 of the 12 different maps in H1. What this means is that here we had assumed that 5 into 5 into 12. So the information is being taken from 12 different maps, but in reality they have only taken 8 over here. Okay. So that's the main difference between H1 and H2. You can see the number of free parameters is 2592 here, which is significantly higher than the number of free parameters that we had for the layer H1. And similarly, we can think on similar lines for layer H3, and then it finally goes to the output, which is classified into either 1, 2, 3, 4, or up to 10 or up to 9 over here. So this is the entire network architecture, and you can just go through this paper once. It is really very nicely and written in very simple words. Uh, the network was trained for 23 passes, and another interesting thing is that it was running on Sun 4260. So, as I referred to before as well, the computational powers back then were not very high, and people had to use the existing machines, and a lot of manual work was involved. That's what makes this paper so significant, actually. It was trained for 23 passes, and then the mean square error uh, really came down as the number of passes increased. Uh, so, just to summarize, some of our main learnings from this entire paper have been that um a new network architecture has been designed in the year 1989, where the entire image is taken as an input in the network. Weight sharing seems to be something that has worked for them. It has significantly reduced the training time. The operation that they have used here is convolution in every single pass. This was very unique at the time, and they mentioned that our work is one of the state of the art. So here, if you can see, our results appear to be state of the art in digit recognition indeed. So this also gives us a sense of the historical evolution of the field of CNN and where we are right now after 3 decades. We are seeing all these beautiful applications, but the foundation was laid down by these researchers, and we should always keep them in our mind before we engage in further AI related activities.